Alright, David Can here with another question from the question bank in the style of what you find in your Hayes and Harris Math SL textbook in Chapter 2E.4. In this question, we're given the first four squares in a sequence of squares which are subdivided in half. We're told that the area of square A here is 1/4. So what we can assume here is that the whole box has an area of 1, and this is 1/4 of the whole box. Taking a look at diagram 2, we see that the opposite quarter is then divided into quarters, one of which is shaded. And the pattern continues into diagram 3. The lowest quarter is divided again into quarters and one is shaded. And again. Following this pattern, we want to try and find the area of squares B and C. All right, so for squares B and C, square B is 1/4 of this quarter. So this is 1/4, and it's 1/4 of that. So the area of square B is 1/4 of 1/4. That's a 1/16. For square C, let's make some room over here. So for part I, that's the area of square B. Now we want the area of square C. Well, this is a 1/16, so this is 1/4 of a 1/16. So that's 1/4 of 1/16. That's 1/64. Part 2 asks us to show that the areas of the squares A, B, and C are in a geometric progression. All right, so that means that the area of square A progresses to the area of square B, progresses to the area of square C by some common ratio. So let's look at those areas. Square A was 1/4, square B was 1/16, and square C was 1/64. Let's see how we progress from here to here. That's 1/16 divided by 1/4, which is 4 on 16, which is 1/4. How about from here to here? 1/64 from 1/16 is 16 on 64. That's also 1/4. So to go from here to here, we multiply by 1/4, and to go from here to here, we multiply by 1/4. So this is a geometric progression because we're multiplying by the same thing every time to go from one term to the next. So then we want to write down the common ratio of the progression. Well, that's easy. We already found it. The common ratio is 1/4. Multiply by 1/4 to go from term to term. So now using that information, we want to find the total area shaded in diagram 2. So this is part B, I. We'll look at diagram 2. Diagram 2 just contains square A and square B. So that's not too hard. That's just the area of A plus the area of B. That's 1/4 plus 1/16. 1/4 is 4/16 plus 1/16 is 5/16. All right, now we want to find the total shaded area in the 8th diagram of this sequence, which isn't shown. Basically, we continue in this way all the way out to the 8th diagram, and we want to add up those 8 squares. Well, we could do it this way, or we could take advantage of geometric series. So the sum of a geometric series is the first term times the common ratio to the power of n take 1 over the common ratio take 1. The first term in this sequence is 1/4, and the common ratio is also 1/4. We want to go all the way out to the 8th term, so we want the sum of the first 8 terms, so that's 1/4 times 1/4 to the power of 8, n is 8, take 1, on 1/4 take 1. Now 1/4 to the power of 8 is not something you'd be expected to do in your head, so you'll punch that into your calculator. The other hint that you're not expected to do this in your head is that the question tells you to give your answer correct to 6 significant figures. You're not going to be expected to do that by hand. So you punch it into your calculator and you get 0.333328. Almost a third. 0.333333 repeating. It's almost a third. So if we kept adding forever, probably the answer is going to be a third. Well, the last part says do that. Find the sum of the infinite geometric series. So the sum of an infinite geometric series is the first term over 1 take the common ratio. The common ratio's absolute value has to be less than 1, but in this case it is. The common ratio is a quarter. We know what U1 is. It's 1/4. And we know what R is. It's 1/4. 1 is 4/4. So 4/4 take 1/4 is 3/4. 1/4 divided by 3/4, the 4's cancel, and we get 1/3. That's the sum. Basically, the black shaded areas are 1/3 of the total area. Looking at this result, that shouldn't be so surprising. And actually, looking at the diagram, that shouldn't be so surprising either. You can imagine 3 cones. A white cone here, a black cone here, and a white cone here. Each of those cones has the same surface area. Here, I'll show you. We have a black square and 2 white squares of even size. A black square and 2 white squares of even size. A black square and 2 white squares of even size. So for every black square, there are 2 white squares that are the same size. So we can see that as this pattern digs down into the corner, 1 out of every 3 regions will be black, and so the sum of the black area is 1/3 of the total.